The following video is on logarithmic differentiation. If f of x equals 2 to the x, then we know that the limit definition of the derivative of f at 0 is given by the limit as h goes to 0 of 2 to the 0 plus h minus 2 to the 0 over h. We can simplify this as 2 to the h minus 1 over h. But then when it comes time to actually evaluating this limit, we actually don't know how to do this. F prime of 1, similarly, is the limit as h goes to 0 of 2 to the 1 plus h minus 2 to the 1 over h, which, notice that we can pull a 2 out of each term, and we're left with the limit as h goes to 0 of 2 times 2 to the h minus 1 over h. This gives me 2 times f prime of 0. We can do the same thing if we're looking at f prime of 2 or f prime of x in general. And in each case, we end up with 2 to the x times f prime of 0. The hard thing, though, is figuring out what is f prime of 0. If f of x equals 3 to the x, we can do the same process. F prime of 0 will be the limit as h goes to 0 of 3 to the 0 plus h minus 3 to the 0 over h, which simplifies to the limit as h goes to 0 of 3 to the h minus 1 over h, which again we don't know how to solve. We can look at f prime of 1, similarly, and notice that we can factor a 3 out of every term in the numerator and get the limit as h goes to 0 of 3 times 3 to the h minus 1 over h, which again is 3 times f prime of 0. We can do the same thing with f prime of 2, all the way up to f prime of x in general, which gives us the limit as h goes to 0 of 3 to the x times 3 to the h minus 1 over h, which is the same as 3 to the x times f prime of 0. Again, though, we don't know how to find f prime of 0. In general, this also works. If f of x is given to us as a to the x, then f prime of x is going to be the limit as h goes to 0 of a to the x plus h minus a to the x over h, which is the limit as h goes to 0 of a to the x times a to the h minus 1 over h, which is a to the x times f prime of 0. But in general, we don't know how to find f prime of 0. We can approximate these limits by plugging in values very close to 0 from both above and below, and we get that the limit as h goes to 0 of 2 to the h minus 1 over h is approximately 0.693147. The limit as h goes to 0 of 3 to the h minus 1 over h is approximately 1.09862 or 8612. So, if d by dx of 2 to the x is approximately 2 to the x times 0.693147, then we know that d by dx of 2 to the x is less than 2 to the x, because we're multiplying 2 to the x by a number that's less than 1, making it smaller. Similarly, we can do the same thing with 3 to the x. The derivative of 3 to the x is 3 to the x times 1.098612, and so d by dx of 3 to the x is greater than 3 to the x, because we're multiplying 3 to the x by something bigger than 1. This leads us to guess that presumably there's a value of a such that a is between 2 and 3, and the derivative of a to the x is equal to a to the x. Suppose a satisfies that d by dx of a to the x equals a to the x. That means that the limit as h goes to 0 of a to the x plus h minus a to the x over h is equal to a to the x. That's the limit definition of the derivative. We can simplify the left-hand side and I'm left with a to the x on both sides. So when I divide that out, I'm left with the limit as h goes to 0 of a to the h minus 1 over h equals 1. So a to the h minus 1 over h is approximately 1. We can do some algebra from there, and we get that a is approximately h plus 1 to the 1 over h power. So putting the limit back in, we get that the limit as h goes to 0 of h plus 1 to the 1 over h power is a. We know what this limit is. This is a familiar limit for us. This limit goes to the value e. So notice that e is approximately 2.71828. So just as we assumed, e is between 2 and 3. So we just showed that d by dx of e to the x is actually equal to e to the x. But we still don't know how to find the derivative of 2 to the x or 3 to the x. We'll take one more detour before we can get there. Let's find the derivative of natural log of x. We know that e to the natural log of x equals x. So taking the derivative of both sides, we end up with the derivative of the outside, which is e to the natural log of x, leave the inside the same, times the derivative of the inside, which is d by dx of natural log of x. And we'll just leave it as that since we don't know what it is. The right-hand side, the derivative of x, is just 1. So we get e to the natural log of x, which is the same as x, times d by dx of ln of x equals 1. And dividing both sides by x, we're left with d by dx of natural log of x equals 1 over x. So therefore, the derivative of natural log is 1 over x. This process is called logarithmic differentiation. The hardest part is just coming up with that initial equation, in this case e to the natural log of x equals x, that allows us to take the derivative and find the value that we're looking for. Now we're finally ready to find d by dx of 2 to the x and d by dx of 3 to the x. Let's start by finding the derivative of 2 to the x. The natural log of 2 to the x is equal to x times the natural log of 2, because one of the properties of logarithms allows us to take the exponent and bring it out front. Taking the derivative of both sides, we get the derivative of natural log, the outside function, is 1 over 2 to the x, times the derivative of the inside function, d by dx of 2 to the x. And the right-hand side, notice that x is the function x, and ln of 2 is just a constant. So the constant stays there, and we take the derivative of x, which gives us 1. So the right-hand side becomes ln of 2 times 1, or ln of 2. Solving for d by dx of 2 to the x, we get d by dx of 2 to the x equals 2 to the x times ln of 2. Notice that ln of 2 is approximately 0.693417, which is exactly that value of the derivative of 2 to the x evaluated at 0. In general, we can find the derivative for a to the x for a greater than 0 using the same exact technique. Everything is exactly the same as before, except instead of the number 2, we have the value a. At the end, we get d by dx of a to the x is equal to a to the x times ln of a.